All right, so this video is going to start our discussion of equilibrium. What you have here is a solution of cobalt 2 chloride that is acidified. Hydrochloric acid has been added to it. You can see that it's purplish color. And when it is placed in different temperatures, we see the color of that solution change. It went from purple to more of a pinkish. And then when it went into hot water, became more bluish. We can also see a change when we add different components of the mixture because the cobalt 2 chloride is found as a hydrate in its solid form. So when you add more hydrochloric acid to it, you see it go more toward the purplish bluish side. And when you add more water to it, you see it go back towards more of the pinkish side. Equilibrium, all of these changes are due to equilibrium. And equilibrium basically is a state where the concentrations of your reactants and products are remaining constant. It's not that they aren't changing, it's just that they are changing at a constant rate. So that the rates of the reactions, which we just got done studying with kinetics, the forward rate and the reverse rate are both occurring, but because they're happening at a constant rate, you don't see any noticeable changes. The reactions will continue in both directions, and they occur spontaneously until they reach a state where they are at equilibrium. The majority of chemical reactions that we have studied are going to favor either the reactants or the products. Reversible reactions can favor either one, and depending on environmental conditions and when equilibriums are disrupted, reactions will shift and result in response to those changes. So it is a very dynamic situation. It is not static. We typically see it represented with an arrow pointing in both directions. So here you see between nitrogen dioxide and dinitrogen tetroxide that depending on the temperature, you will see one form, when you're at a higher temperature, we see more N2O4s. Sorry, we see more NO2s, and when you're at a lower temperature, we see more of the N2O4s. But you have both present. So going back to kinetics, we talked about rates of a reaction and how product rates increased and reactant rates decreased as the reaction proceeded. While that part's going on, that is the kinetics component of your reaction. But when the rates plateau, when the rates become relatively constant, that is when you have reached equilibrium, where you will no longer see any appreciable change because the rate at which the products are formed is constant and the rate at which the reactants are being consumed is also constant. So one thing you're probably really going to like about equilibrium is that when we write an equilibrium expression, you are going to take it, you're going to use the stoichiometry of your equation to express how the reactants and products relate to one another. K is your equilibrium constant. It can be written as Kc or as Keq. Kc is for concentration, Keq is just the standard equilibrium. But all of these are compared to concentrations of 1 molar, so K itself is unitless. It is dependent on temperature. As temperature changes, your value of K will change. So your concentrations are raised to their coefficients. We only include, your substances that are able to have concentration changes as a result of temperature changes. And so that's going to be your gases and your aqueous solutions. Your solids and liquids, being incompressible, will never be included in an equilibrium expression. So you'll never see aluminum as a solid. You would never see pure water as a liquid, but you could see a solution of aluminum chloride be included in your equilibrium expression, or you could see a gas such as oxygen be included in your equilibrium expression. If we are expressing equilibriums with gases, with pressures, we typically will write them not in the concentration brackets as you saw on the previous slide, but with partial pressures. Regardless, whether you're dealing with K, Kc, or Keq, which all mean the same thing, or Kp, which is just the K associated with pressures, you will not have any units associated with your K. Before there were changes made, there's a relationship we can use to relate Kp to K. Y'all aren't going to have to cover that this year. So we're going to write equilibrium expressions. So these are going to be the ones with the concentrations for these gas phase reactions. Even though they're gases, we can still write them in terms of concentrations, and it's always products over reactants. So in the one on the left, I would take the concentration of carbon monoxide, multiply it by the concentration of chlorine. They're both coefficients of 1, and I would divide it by the concentration of my reactant, COCl2. All of those had coefficients of 1, so that's why you see no exponents in my equilibrium constant expression. On the right side there with the ammonia decomposition, you do see coefficients with ammonia and hydrogen. So you would still take the concentration of nitrogen and you would still take the concentration of hydrogen, but you need to cube that one, and then you would divide it by the concentration of ammonia squared. And again, if any of those reactants or products had been solids or liquids, they would not be included in your equilibrium expression. So if we write those same expressions for KPs, we would use partial pressures. We can do that. All these are gases. You will not be asked to write a KP expression for an equation that does not involve gases. Everything's going to look exactly the same as what we did on the previous slide, but rather than using concentrations, we use partial pressures. So here we're starting to encounter some reactions that do not just have substances that are included in your equilibrium expression. They have some solids or some liquids. So in this first K expression, we have a solid as a reactant and a solid as a product. So when we write our equilibrium expression, the numerator would just have a 1 because the only product cannot be written as part of your equilibrium expression. But oxygen can be included. It had a coefficient of 3/2, so that's what it would be raised to. With your partial pressure that are going to be used in the second equation, again, you can't write your product in your equilibrium expression, but you can write the one reactant CO2. So it would be the partial pressure of CO2. We can relate equilibrium constants for similar reactions to one another. If our equilibrium expression is going to be the reciprocal, basically if the reactants and products have switched sides, then the value of K would just be the inverse of the original K. Or if we have changed our components, our coefficients of our reaction by a factor, we can adjust our K by that same factor as well. So here we have a reaction where hydrogen and bromine make two hydrogen bromide gas molecules, and you're given the K value for that expression. Now I want to know what Kp would be if I had two similar reactions. So if I look at the one on the left, I see that compared to my first reaction, HBr is now on the reactant side as opposed to the product, so it's the inverse. But I also have half the amount of HBr that I had in my original reaction. So for this first expression, I think first of all, I'm just writing what the Kp would be like. That you would have, if I go back to that parent reaction, HBr would be squared over hydrogen and bromine. In my reaction on the left, I have the same equation, but it's the inverse, and the coefficients have been changed by a factor of 1/2. So to calculate the new K, I would take that original K, take the square root of it, and take the inverse of that value. And when I do that math, I get that the new K has an equilibrium value, an equilibrium constant of 5.3 times 10 to the negative third. If I do this for reaction 2, I see that it's the exact same reactants and the exact same products, but the coefficients have been doubled. So I would need to square my original equilibrium constant. And when I do that, I see that my equilibrium constant is 1.2 times 10 to the 9th. So I've shown you some values with large exponents and some values with small exponents. Why the heck do they have different size exponents? What does that mean? When your K is substantially greater than 1, when there's a very large positive exponent, your products are going to be favored more than your reactants. You would need to have greater concentrations in your numerator where your products are found in that equilibrium constant expression compared to your reactants. If it is much less than 1 at equilibrium, then your reactants are being favored. You're not forming a whole lot of products. And if you happen to be exactly at 1, this does not happen very often, but if you happen to be exactly at 1, then there is an equal distribution and equal favoring at equilibrium for both the reactants and the products. So there you see the product favored. Products have a much greater concentration. The reactant favored. The reactants have a much greater concentration. We see that sometimes with acids that don't want to dissociate a whole lot. We also can see that with precipitates that don't want to separate from their ions. But we won't see a whole lot of that in between where they're equal to 1. We can use these equilibrium constants to compare initial concentrations of our reactants and products to determine if our reaction is at equilibrium, if we still need to form more products to reach equilibrium, or if we have gone past our equilibrium, we kind of need to go back. We need to make more reactants in order to reestablish equilibrium. So Q is going to be set up the same way as K. It's a reaction quotient, and it's comparing the initial concentrations to your equilibrium concentrations. When Q and K are equal, you are at equilibrium, and there is no need for reactants to form products or products to form reactants. The rates are constant. If Q, if you have, is greater than K, that means that you have more reactants in that solution than you need. You need to form more products. You need to increase the rate of the forward reaction and decrease the rate of the reverse reaction. You need to form more products in order to reach equilibrium. If Q is less than K, you need to take some of those products and break them back down. You've allowed the rate of that, or the reaction rate for the products has gotten too large and it needs to decrease to reestablish and form more reactants. So we have here a K value, 2.4 times 10 to the third for this reaction, and we are given partial pressures for the 3 components making up our reaction, NO, N2, and O2. We want to know, is this at equilibrium, and if it's not, in which direction will the reaction need to shift? Will it need to make more products, or will it need to make more reactants to reestablish equilibrium, or to establish it for the first place? So first thing we want to do is write an equilibrium constant expression so that we know how these quantities relate to one another. The 2 products both raised to the power of 1 over the 1 reactant squared. When we substitute these values in and we calculate Q, we get that our Q is 2.2 times 10 to the third. For sig figs purposes, I just use the sig figs in my concentrations. The one with the smallest number determines what my value of Q would be. This Q is slightly smaller than my K equilibrium constant, so I have not yet reached equilibrium, which means I will need to produce more products. I will have to shift the reaction so that the reactants get consumed, and the products will need to be formed until Q is able to be equal to K. I haven't quite made it to that point yet where the rate of the forward reaction and the rate of the reverse reaction are constant. In my second set of data, I have different concentrations of my reactant and my products. When I calculate my Q this time, it is larger than my K value. And so I have made more products than I would have expected to make if I'm going to be at equilibrium. I need to consume some of those products to reestablish equilibrium. And I would do that by having an increase in my reverse reaction rate so that I can produce more reactants until I reach a point where the rates of the forward reaction and the rate of the reverse reaction are constant. So you've seen one where it's less, you've seen one where it's greater. I'm guessing you can figure out what's going to happen with this one. It should, if I've done the math right, this one should fall right on with these particular partial pressures. Because Q was equal to K, we have reached equilibrium and there is no shift needed.